Students, welcome back to the 18th episode of Solving 45 Expected Questions Daily for NEET 2025, which will also benefit NEET 2026 aspirants. Today, we're covering a key topic in physical chemistry, equilibrium, where understanding balance is not just essential in chemistry, but in your preparation too. With only 11 days left for your NEET 2025, every minute counts. Also, a quick update. Tomorrow will be the final episode of this rapid 45 question series, and we'll wrap it up with the important topic thermodynamics. After that, get ready for daily full length mock tests covering all topics to supercharge your final revision. And remember, equilibrium is all about balance, and so is success. Stay calm, stay focused, and let your hard work speak in the exam. Let us begin. The first question: if 1 mole of iodine is introduced into 1 liter flask at 1000 Kelvin at equilibrium, the equilibrium constant is given as micro. Which one is correct? You are given different options. Let us calculate from this given conditions. So iodine, it is in equilibrium. So when this dissociates, it now gives 2 particles of iodide. Let us say after equilibrium is maintained, this is the molar concentration. Now equilibrium constant can be found out from the law of chemical equilibrium. By applying that law, we now have this new relation because the stoichiometric coefficient should be raised to the power, and quotient is given 10 to the power minus 6 as the equilibrium constant. Now solution shows that this 1 minus x is greater than twice x, and iodine gas is greater than iodide. So from this we can conclude that option A would be the answer to question number 1. I hope it is understood. Let us read question number 2. In a reaction, A plus twice B generate 2C, 2.0 mole of A, 3.0 mole of B, and 2.0 mole of C are placed in a 2-liter flask, and the equilibrium concentration of C is 0.5 mole per liter. The equilibrium constant K for the reaction is. Now let us write the reaction to answer this question. Twice B and A plus gives 2C. This is the given reaction. Now let us draw the ICE chart. In the initial moles, we have 2 liters. So initially we have 2 liters, and this would correspond to 3 mole because question is given 3 mole of B, and now you have 2 moles of C. So this is the initial mole concentration. At equilibrium, the moles in 2 liters would now be changed to, if 0.5 is formed as a product, so 2 times of 0.5 would be 1, and 4, because 0.5 has changed to the product. 0.5 into 2, it is 4. Then this would be 2.5. The molar concentration moles in 2 liters would now be, this is in equilibrium. This is initial equilibrium, and let us say the concentration required in 2 liters. This will give 1.25, 2, and now you have 0.5. Applying the law of chemical equilibrium, equilibrium constant Kc should be equals to 0.5 square divided by 1.25 times 2 square. So You can cancel by 5. 5, 5. 525 is 125. And into square will be approximately 50.05. So option C would be the answer to question number 2. Moving on to the next question number 3. The equilibrium constant for the reaction nitrogen and oxygen gives nitric oxide at 300 Kelvin 4 micro is the equilibrium constant. What is Kp for the above reaction? And you remember this gas constant is in calorie. So you should be very careful in solving the questions. But for this particular question is given what is Kp for this relation. So you know the relation between Kp and Kc, which is RT to the power change in gases moles. So when you check, the change in gases mole would be 0. So anything raised to the power 0 is 1. So we now have Kp equals to Kc. So the given Kc would be also the value of Kp. So question number 3 would be option B is the answer. Moving on to the next question, number 4. The standard Gibbs free energy for the reaction X plus Y gives Z is negative 4.606 kilocalorie. The equilibrium constant for the reaction at 227 degrees Celsius is. So what is the relation between delta G and G naught? We know that the relation is 2.303 RT log reaction quotient. So when equilibrium is attained, Q becomes Kc and del G becomes 0. So the new relation between delta G naught and this equilibrium constant would be 2.303 RT log Kc. I hope it's clear. So simply substitute the values, whatever given in the question, 0.06. And since this is in terms of kilo, power 3 minus 2.303 into gas constant is R, which is in terms of calorie, it will be 2. 500 is the, because I have converted by addition of 273, the Kelvin temperature would be 500 and log Kc. See, to find this, you need to know the anti-log value, which I have explained in the shorts. Log Kc is equals to minus 4.606 10 to the power 3 minus 2.303 into 1000. Cancel this. You get 2. Right? So what is anti-log? Anti-log of 2, that will give you equilibrium constant. See, to find the anti-log, just raise to the power 10. So what is this? 100. There is a short which I have created. You can check it out to find the anti-log without using table or calculator. This will be very helpful in your exam. So we have 100 as the value of equilibrium constant. Let us read question number 5. The equilibrium constant for the reaction sulfur dioxide is the product, and equilibrium constant is 4.9 centi. The value of Kc for the reaction, the reverse reaction, you should check the stoichiometric coefficients. So whenever there is reversal of the reaction, the equilibrium constant is also affected. And not only that, when the stoichiometric coefficient is multiplied with any variable that is raised to the power. So for this particular reaction, the Kc value is 4.9. I hope it's clear. So on taking the square of the above reaction, what would be the new value of this? the square would be 4.9 into 10 to the power minus 2 square. So near value would be approximately 24.01 into 10 to the power minus 4 because you're taking the square root of 4.9. And for this new value, that is sulfur dioxide and oxygen giving sulfur trioxide gas, it would be the reciprocal because you're reversing. So simply take the reverse of this, minus 4 becomes 10 to the power 4 by 24. Cancel, you can easily cancel this by 216, 416. So answer would be option C. I hope it's clear. Let's read question number 6. This is about acid and base question. Remember, a strong acid have weak conjugate base and vice versa. So looking at this question, the correct order of the strength of the acid given above would be the one which contains fluorine would be the highest. Let us now do the ranking here separately. Then followed by hydronium. The rapid tendency to release the hydrogen would be the strongest. Followed by this bisulfate and bicarbonate. You know, bicarbonate is a very weak acid. It is present in our system, living body system, as carbonic acid. Option would be 1, 3, 2, 4. 4 would be the strongest acid. So looking at this trend, you can consider option C as the answer for question number 6. Let us read question number 7. The degree of dissociation of dinitrogen tetroxide. Actually, this is a dimerization. The reverse will be dissociation of this dinitrogen tetroxide, giving your dinitrogen dioxide. So let us build up an equation for the dissociation of dinitrogen tetroxide to generate 2 moles of nitrogen dioxide. If alpha is the degree of dissociation, you have twice alpha. So what is the total mole? 1 plus. So cancel this alpha and alpha, you get 1 plus alpha. So using the, okay, let me write somewhere here because the space is limited. Partial pressure of nitrogen dioxide with respect to dinitrogen. This is the law of chemical equilibrium in terms of partial pressure. Now, since it is given 2 alpha 1 plus alpha, this would be the value. Multiply this with your pressure. Since it is square, take the square. 1 minus alpha divided by 1 plus alpha into pressure. So after simplification, you would be getting 2 to the 4 alpha square P 1 minus alpha. So the most near combination would be option D is the answer for question number 7. I hope it is clear. Let us again check question number 8. The equilibrium constant P1 and P2 for the above reactions, X changing to Y, Z giving P plus Q respectively are in the ratio of 1:9. If the degree of dissociation of X and Z be equal, then the ratio of total pressure at this equilibria is. So let us see that the initial moles of X be taken as A, small a, and that of Z be B. Then for this particular reaction, we have X change to Y. So let us say the initial moles and the equilibrium moles. So since it is dissociating, we will consider here 0. And at equilibrium, we are going to consider, if we start from A mole, it would be 1 minus alpha. And here it would be 2 times of A into alpha. So what is the overall mole or the total number of moles after dissociation? Let us write here somewhere total number of moles after dissociation. It would be A, this is A, 1 minus alpha plus twice A into alpha. So A minus A into alpha plus twice A into alpha. So this is the new equation you have. You can subtract this. Take the common A 1 plus alpha. This is the new value of the number of moles we have by far. Next step, I'm right here at the bottom. The equilibrium constant Kp1, let us say. It would be the ratio of number of moles of Y with respect to X square the total pressure and the sum of the number of moles and the change in the gas moles. So this would correspond to 2A alpha square total pressure and total number of moles as calculated from the above equation would correspond to 1 minus alpha A 1 plus alpha. So this is the equation we have so far, right? So when we take the ratio of this total pressure 1 and total pressure 2, let us erase all this for the next step. And for this next reaction given Z and giving P plus Q, let us consider the initial moles at initial as 0 for P and Q. This will be 0, 0. At equilibrium, we have considered B as the number of moles. So 1 minus alpha B alpha. This is the new equation for dissociation of Z. So let me shorten one step here. What would be the total number of moles after dissociation? B minus B alpha, B alpha, B alpha gets cancelled and B alpha is also present here. So the overall number of moles after dissociation would be B 1 plus alpha. Now in the same manner we can find Kp2, which is NQ into NP divided by the total number of moles for Z multiplied with the pressure, then overall mole delta N. So simplifying this, now you would be getting Kp2, which is B alpha Pt2 divided by B1 minus alpha B1 plus alpha. So the ratio of this, initially we have calculated for this X giving 2Y as Kp1. Now that we are finding for Z giving P and Q as Kp2. So the ratio would give rise to, cancel all the like terms. We are now getting 4Pt1 divided by Pt2. So the required ratio, because the given Kp1 and Kp2 is given as 1:9, let us say 1 by 9. So the new ratio of their pressure would T1 by T2, total pressure T2 would be 4,936, so it would be 1 by 36. 1:36 would be the answer for question number 8. Quite lengthy, but it was worth solving the question. Important question it is. Anyway, let us read question number 9. The dissociation of a gas AB2 at equilibrium can be represented as AB2 dissociating AB and B2 molecule. The degree of dissociation is X and it is small compared to 1. The expression relating the degree of dissociation X with equilibrium constant Kp and total pressure P is given as. So for this reaction, shall we write the, okay, let us consider this is the given reaction. Anyway, let us rewrite this so that we can calculate easier. So this is the question. The given equation is, now we have B2 gas. So at equilibrium, it would be 1 minus X 2 times. Here you have twice x, and x is the number of moles at equilibrium. So what you have to do now is find Kc. Kc, it would be twice x square into x to 1 minus x whole square. So this term, that is x cubed, 1 minus x, can be neglected in the denominator because 1 minus x, it would be a very small quantity. And this, the partial pressure at equilibrium are calculated on the basis of total number of moles at equilibrium. Now the total number of moles that is going to be left, shall we write here? Okay. Total number of moles would now be equals to 1 minus x plus twice x plus x. This would correspond to 2 plus x. So the pressure of AB2 gas would be 1 minus x divided by 2 plus x into pressure. So where this P is representing the total pressure. So in the same way, we can find the pressure for AB as well as B2. So AB would be twice x. Okay, from where I'm getting all this is I'm getting the reference from the equation, all right? No need to have any confusion regarding this. 2 plus x into pressure. In the same way, B2 would be x divided by 2 plus x into pressure. So since this x is very small, so we can neglect in the denominator. So after neglecting, let me erase all this. The new equation we are going to get is, if you have missed any part, you can rewind back and look back again whatever equations that we have built so far. So after neglecting the terms, we have 1 minus x into p. And neglecting this term, we also now generate x into p from the denominator because it is a very negligible quantity. B2, it will now give x by 2 into pressure. So the equilibrium constant can now be found out by after knowing all these values, and substitution gives for PaB2, PB2 and PaB2. So it is going to generate a new equation, P square into P. See, the equation may seem quite exhaustive and lengthy, but once you get the idea behind this, it is not that difficult as we think. It is just a simplification process. P square. And this 1 minus x is a negligible quantity. We have already neglected it. So after neglecting the terms, we now have x cubed P2. So how can you relate x again? You transpose whatever terms that is going to be resolved and take the cube root of this. So you have x equals to twice kp by p cube root. What is the answer for this question then? The answer would be option B is the nearest answer for question 9. I hope it is clear. Let us read question number 10. The exothermic formation of chlorotrifluoride is represented by the equation. You have the reaction between chlorine and fluorine. It is an interhalogen compound, and you guess out what is the shape or geometry. This can be linked with the chapter from chemical bonding by using the valence cell electronic pair repulsion theory. So anyway, this reaction is given as an exothermic reaction. Thus, according to the Chatelain principle, lowering of the temperature and addition of fluorine and chlorine favors the forward direction, and hence the production of this chlorine trifluoride will be more favored. So apply the Chatelain principle and the option would be A. Let us match the column for question number 11. QA greater than less than QC. QC greater than QC. KC, sorry. So A would be linked with no reaction would take place. No, this is not. Reaction goes to the right. Okay. Just imagine this Kc is just like the hour hand. Whenever it is in the 12 o'clock position, it is equilibrium. When it is on the right side, it is going in the spontaneous. When it is on the left side, it is non-spontaneous. So it means basically when Kc is on the right side, it means it is dominant than Qc. So it is favoring a spontaneous process, and if it falls back, it generally means Qc is dominating, and at equilibrium it is generated as 0. Okay, so from this we can see net reaction goes from left to right. Qc is greater than less than Kc. Same thing, you apply the same logic. If Qc is greater than Kc, it would go backward. So net reaction goes to the left from the right side. And if it is equilibrium, no reaction would take place. So A2, B1, C3, D would be the answer for question 11. Clear? Right. So let us read again the next question. Which of the following are correct? Delta G is negative, is a spontaneous. This is correct. Let us read some more options. Delta G is positive, then the reaction is non-spontaneous. This is also correct. Delta G is 0, then reaction. So if 1, 2, 3 are all correct, A would be the answer for question number 12. Question number 13. On the basis of Le Chatelier's principle, predict which of the following condition would be unfavorable for the formation of sulfur trioxide given that it is an exothermic process. Right, so since this reaction is an exothermic process, hence the lower temperature will be favored for formation of the forward reaction, and also the volume is decreased by applying high pressure. So 13, C is the answer. It's a fast revision episode, so we need to go faster. Let's read question number 14. The standard Gibbs energy change at 300 Kelvin for the reaction twice A changing to B plus C is 2494.2 joule at a given time. The composition of the reaction mixture A is half, B is 2, C is half. The reaction proceeds in which direction? So simply apply the value of reaction quotient Q. You have B and C divided by A square. So 2 into 1 by 2 divided by 1 by 2 square will be 4. So this is the value of reaction quotient you have so far. And the relation between Gibbs free energy would be delta G naught equals 2 minus 2.303. Gas constant is 8.314. And temperature is 300 log of Kc. So find this log of Kc. And what is the value of delta G naught? 2494. So cancel this with 8 and 2. 1, 2, 4, 7 divided by 8. 1, 2, 4, 7 divided by 8. It is a multiple of 3. So since there are 3 zeros, log Kc would be approximately minus 0.434. So as I have told before, without using the table, you can easily find the antilog values. So Kc would be roughly 0.37. So we have Q is greater than Kc. So answer would be the reverse direction because Q is greater than Kc. D is the answer for question 14. Moving on to question number 15. If the equilibrium constant for nitrogen and oxygen reacting to give nitric oxide is K, the equilibrium constant for this reaction will be. So nitrogen and oxygen gives 2 moles of nitric oxide. These are all in the gaseous state. So K would be, if I write the equilibrium constant, square N2 O2. Reversing the reaction, after reversal, let us say K prime This would be N naught. I'm writing the equilibrium constant for the next equation. Power half, because the stoichiometric coefficient is reduced by half, so it would be root over k, because you have to multiply the stoichiometric coefficient to the new equation you have generated. So 15 answer would be A is the answer to question number 15. I hope it is clear. Let's read question number 16. The following reaction is performed at 298 Kelvin. Nitric oxide is undergoing oxidation to generate the new oxide of nitrogen dioxide. The free standard gives free energy of nitric oxide is 86.6 kilojoule per mole at room temperature. What is the standard free energy of formation of nitrogen dioxide at room temperature? Given Kp is 1.6, 10 to the power 12 tera. So to find this question answer, you have to subtract the values for these two given gives free energy. That is, whatever you have here, delta G naught. The stoichiometric coefficient is 2 for delta G naught, nitrogen dioxide. The reversal of this gives delta G naught multiplied 2 times. This is for nitrogen dioxide. And delta G naught and nitric oxide would give RT, that is 298. And ln Kc would be 1.6 10 to the power 12. Again, substitute the values of nitric oxide and nitrogen dioxide gives free energy. So the new equation would be 2 into delta G naught. This is for nitrogen dioxide minus 2 into, it is given here 86.6 kilojoules. So simply generate into joule, it would give 86,600 equal to minus R room temperature ln 1.6 into 10 to the power 12. Right. So from this, you can easily get the value of delta G naught for nitrogen dioxide. So it would correspond to, after simplifying, 0.5, 2 into 86,600 minus R room temperature. And you need not find all this, because if you look at the options, they have given some values. So correspond to that, you have option B is the answer for question number 16. I hope this is clear. Let's read question number 17. Which of the following pairs constitutes a buffer? Nitric acid is a weak acid and sodium nitrite is a salt of that weak acid and a strong base. So this is sodium hydroxide. So it constitutes a buffer. So option D is the answer for question 17. Easy. Question number 18. For dibasic acid, correct order is: in dibasic acid, the loss of the second proton occurs much less readily than the first. Usually, the dissociation constant values for the successive loss of protons from these acids differ by at least a factor of milli, that is 10 to the power minus 3. That is, your dissociation constant A1 should be greater than A2. So considering these facts, since it is a dibasic acid, you should have 2 protons, and after losing this, yes, it should look something like this. After losing again, proton and minus 2. So this is a required expression for Ka1, Ka2. So after this simplification, we can now say that Ka1 is much stronger than Ka2. This is there in your theory and your NCERT text. Question number 19. The expression delta G is equal to minus RT ln Kp plus RT ln Qp, and select the correct statement at equilibrium. So Van Hoff reaction isotherm is given as, the reaction scheme is delta G equals delta G naught plus RT ln QP. So when the reaction is in a state of equilibrium, the free energy would be zero. So the standard gas free energy would be minus RT ln QP. And this QP would change to minus RT ln KP. So we can rewrite delta G naught is minus RT ln KP. So B is the answer for question number 19. This is clear. Let us see question number 20. Kc for dissociation of phosphorus pentachloride giving PCl3 and chlorine gas is 0.04 at 250 degrees Celsius. How many moles of PCl5 must be added to a 3-liter flask to obtain a chlorine concentration of 0.15 molarity? So at equilibrium, the moles of chlorine must be 0.15, this much value chlorine. Okay, you have to multiply with this with 3 because the number of moles, as you know, molarity is mole per liter and mole is molarity into volume. Now the moles of chlorine must be 0.15 into 3. That means it is 15 3 is 45. So 0.45. This is the number of moles. So let us rewrite the equation so as to make it easier. Cl3 and chlorine gas. So 0.45. This is the number of moles. Okay. At equilibrium concentration. So what is Kc? Now you have these values, the concentration. You can now find Kc easily. So PCl3 multiplied with this chlorine, PCl5, you would be obtaining 0.04 equals to 0.15 into 0.15 divided by x minus 0.45, 3. Simplify this, and when you transpose this on the right side, multiply again 3x. So 3 into 15, 45 into 15, it will be divided by 2x now be equals to approximately 2.1 moles. 20, option B is the answer. I hope it is clear. Let us start question number 21. In the following hypothetical reaction, yes, A and B gives C and D. Initial moles of A are twice that of B, and at equilibrium moles of B and C, they are equal. Percentage of B reacted is how much? So let us write the reaction somewhere here. A and B gives you C and D. So this is the equation. Now we have twice A plus A at equilibrium. It would be, if X is the number of moles dissociated, it would be twice X, and this would all be X. So at the given condition, A minus 3X would be equals to twice X. This is equals, because at equilibrium moles of this B and C are equal. So this is the concentration, the number of moles of B, and this is C. So I have chosen this two. They are found to be equal as per the given questions. Okay, this, let us say, by question. So from this, can you now find X? Yes, it is A by 5. And the percentage of this B reacted, how much? Let us calculate. Let us say 3x by A into 100. So this would be 3 by A. X is already calculated as A by 5. A and it gets cancelled, 100. So 5 into 20, you have now 60 percentage. Good. So the answer would be option A. I hope this is clear and understood. Moving on to the next question, number 22. Which of the following can act both as Bronsted acid and Bronsted base? Yeah, amphoteric in one case. You can consider. So this bicarbonate can donate as well as accept proton. You can write if you would like to. Carbonate would be bicarbonate and a proton, right? Okay. And further, you can also generate. So this is the answer. Question number 22C is the answer. Question number 23. It's a match the column type. You know the relation Kp equals to Kc RT delta Ng. So using the relationship, you find A. So for this reaction, what is delta Ng? It is delta Ng is negative, so we can say, why I'm saying negative, it is because 2 minus 4, it is minus 2. So Kp and Kc. Kp would be less than Kc in this case. And for this second option, delta Ng is greater than 0, positive. And in the third condition, delta N will be 1. Okay. And for this esterification, it does not contain any gas, so we are not going to count for this. So let us simplify this again. A would be 2, B would be 1, C 4, D 3. So A2, B1, C4, D3, A would be the answer for question 23. Hope it is clear. Let's read question number 24. Which of the following statements are correct? Ionic product of water. Yes, this is correct. At 298 Kelvin. Statement 2 would be wrong. Right? And Kw does not depend upon temperature. This is wrong. Molarity of pure water is 55.55. Yes, because 1000 divided by 18 is 55.55. So since this Kw that depends upon temperature, it is an equilibrium constant. So C. Option C, that is 1 and 4 would be correct. So C is the answer for question 24. 25. At a certain temperature, the dissociation constant of formic acid and acetic acid are 1.8 10 to the power minus 4 and 1.8 10 to the power minus 6 respectively. The concentration of acetic acid solution in which the hydrogen ion has the same concentration as in 0.001 molar formic acid solution is equal to. So this question is based on Oswald's dilution law. We can say root over Ka into C. We can generate 0.001, 1.8 into 10 to the power minus 4. This is for formic acid. And for acetic acid, let us keep the concentration as C2 into 1.8 into 10 to the power minus 5. This is for, okay, let's write here formic acid. And this is for acetic acid. So equating and solving, we have to find C2. So after equating and solving these two equations, we can now find the value of C2. 1.8, take the square root out, you can cancel this. This is minus 5, minus 4 gets cancelled, but the remainder is minus 1. Here another 0.001 is still present, so after equating, C2 can be 0.01 molar concentration. So 25 related option B is the answer for question number 25. Moving on to question number 26. The first and second dissociation constant of acid A are given. H2A is the dibasic acid and 1.0 10 to the power minus 5 and 5.0 10 to the power minus 10 respectively. These are the dissociation constant for the first and the second. The overall dissociation constant of the acid will be, so apply the rule of the thumb. Ka1 is given as 1 into 10 to the power minus 5 and Ka2 is given as 5 into 10 to the power minus 10. So simply multiply this two value, K1 into K2. So after multiplying this, you have 5 into 10 to the power minus 15. This would be the answer. So when a reaction has two types of dissociation constant, but the overall reaction is the same, you can simply multiply the equilibrium or the dissociation constants in the successive steps. Question 27 says equal volumes of three acids solutions of pH 3, 4 and 5. The acidity keeps on decreasing. They are mixed in a vessel. What will be the hydrogen ion concentration in the mixture? So for this hydronium ion for a solution having pH equals to 3, it is given by, the definition is negative logarithm of hydrogen ion. That is the definition of pH given by Mr. Sorensen. So from that definition itself, we can now get the value of concentration for hydronium as, yes, minus 3 can be in terms of mole per liter, because as you know, hydronium ion concentration can now be written as 10 to the power minus pH, right? In the same way, for the solution having pH 4, it will be 10 to the power minus 4, and for pH 5, it will be 10 to the power minus 5. So looking at this concentration values, let us keep the volume of each solution to be 1 liter, and the total volume of the mixture would now be equals to, let us write here, volume total would be 3 liter for each of the successive 3 acid solutions. And the total ion present in the mixture solution would now be equals to the sum of all this, that is minus 3, minus 4, minus 5. Now the hydrogen ion or the hydronium ion concentration of mixture solution would be divided by the total volume, because molarity is defined as mole per total volume per total mole by total volume. So this would be, take the, you add this minus 5, minus 4, minus 3 subsequently, you would be getting a 5-digit number, 111 by 3. Divide this by 3, it would be 3.7 10 to the power minus 4 molar concentration. So question number 27, option would be B. 3.7 10 to the power minus 3 molar concentration is the answer for question number 27. Moving on to question 28, the solubility product of silver chloride is 4.0 10 to the power minus 10 at room temperature. The solubility of silver chloride in 0.04 molar calcium chloride will be. So you know the relation between Ksp and S, right? So can I say Ksp is the product of the molar concentration of the salts? From this we can find the silver ion concentration as Ksp by chloride. So this would be equals to 4 into 10 to the power minus 10 divided by 0.08. This is the concentration of chloride. So cancel this approximately, because 8 5s are 40, 10 to the power minus 9 molarity. Question number 28, option C would be the answer for this question. The pH of a buffer containing equal molar concentration of a weak base and its chloride. The dissociation constant for base is 2 into 10 to the power minus 5. You have log 2 as 0.3. So use the Henderson's-Hasselbalch equation, that is pOH equals to negative logarithm of dissociation constant of base plus log of salt by base. This is the Henderson's equation, and this log salt by base is equals to 1. So we now have the negative log of base, Kb. This is again equals to log 2, given is minus 5 from this. So simply calculate the value of log Kb. You will be getting minus minus gets cancelled, 5 into 0.301. Okay, let us simplify. Let us say it was 4.7. Now pH and pOH, the sum is equals to always 14. So what is the value of pH? It would be 14 minus 4.7. It would be 9.3. So the pH of the buffer would be 9.3. Option 29 is the answer. In a saturated solution of sparingly soluble strong electrolyte silver iodide, the equilibrium which is set is given if the solubility product constant of silver iodide at a given temperature is 1 into 10 to the power minus 8. What is the mass of silver iodide contained in the 100 ml of its saturated solution? So let us say that the solubility S is S is defined as the maximum amount of solute that can be dissolved in 100 gram of the solvent at a particular temperature. It has many factors which affects it, temperature, pressure, etc. So let us consider this S as the solubility, and the dissociation of this silver iodide gives you silver ion and iodide. Okay, so from this we can find Ksp equals silver ion, iodide ion. So if I consider S as the solubility, we have S square. And given Ksp is how much? Ksp is given as 1 into 10 to the power minus 8. Okay, let me write at the bottom because there's some more space. Ksp can now be introduced inside the square root 1 point minus 8. So after this, you will be getting 10 to the power minus 4 because root over is present. So this much value. And the molecular mass of the silver iodide is 283. So you have to again multiply with that so as to convert from mole per liter to grams per liter, because to convert from mole to gram per liter, you need to multiply with the atomic mass or the molecular mass again. Now the resultant in terms of gram per ml would be 1 into 10 to the power minus 4. 283 is the molecular mass of silver iodide, and in terms of gram per ml, you need to convert this. Question is giving you 100 ml, so 1000 divided approximately 2.83 10 to the power minus 3 gram per 100 ml. This is the answer for question number 30. Answer would be option C. Okay, let's read question 31. What is the hydrogen ion concentration in mole per liter of a solution that is 0.20 molar in sodium acetate and 0.10 molar in acetic acid? The dissociation constant of acid for acetic acid is 1.8 penty. So 31 would be calculated by using Henderson's equation, because whenever buffer is present, we can use this relation pKa plus log salt by acid. Clear? So this is Henderson's equation, and by application of the definition, that is negative logarithm of hydrogen ion, I have removed the negative part and then introduced here inside. So salt by acid concentration. So we can now find H, that is hydrogen ion concentration, which would be Ka into, because I have removed log, because whenever there is negative sign, you can take the division form of this. So it will now be referred as acid by salt. You know this, right? So when you take log on this, you will again generate back here this equation. So I have removed log and I have got the new expression. We're making things simpler. Multiply this with minus 5 into what we have here, 0.1 by 0.2. So we can cancel this by 9 minus 6. 9 into 10 to the power minus 6 is the answer for question number 31. D is the answer. Question number 31. 32. The Ksp for chromium hydroxide is 1.6 10 to the power minus 30. The solubility of this compound in water is. So chromium hydroxide gives chromium ion plus 3 hydroxide. These are aqueous state. So if I consider S as the solubility, 3S. So simply multiply this, you get Ksp value. What is the cube of this 3 to 27? The answer will be 27S for Ksp. So what would be the answer? S would be Ksp divided by 27, 1 by 4th root. So substitute the values, minus 30 by 27, 1 by 4th. So we need not further calculate because it's already there in the question. B is the answer for this question. 33. For the reaction of formation of carbon dioxide, Kp by Kc is. So we have the relation Kp equals to Kc RT delta N. So what is this delta N? It is 1 minus, you have to, take the value of product. Delta N is equals to Np minus Nr. Okay, so 1 minus 1 plus 2. Calculate this, it is minus half, right? So the ratio of Kp by Kc would be RT to the power minus half. Answer is option C. Okay, I hope this is clear. Let's read again question 34. For the reaction nitrogen dioxide giving nitric oxide and oxygen, when Kp and Kc are compared, it is found that which of the following is a statement. So for the reaction given, it is evident that this delta Ng is, just go with this formula, Np minus Nr. So whenever this value is greater than 0, here we have value of delta N is 1. So whenever it is greater than 0, always remember Kp is greater than Kc. So 34 B, 34 would be D. Okay, D is the answer. 35. A monobasic acid has a molarity 0.005 and pH 5. What is the percentage of ionization in this salt solution? So whenever question becomes lengthy or it's confusing, never get mixed up. You should not get lost with the question. Try to decode what the question is asking. The question will have the simplest solution. Looking at this question again, since it is a monobasic acid, we have only one hydrogen atom, and after dissociation you have this proton. The dissociation constant is given as H plus, A minus, and the salt, monobasic acid. Okay, so since this hydrogen ion, we can refer from the Henderson's equation that Sorensen definition that pH is defined as the negative logarithm of hydrogen ion. Hydrogen can now be raised to the power of 10 as negative. So in this way you can correlate with one another. Okay, so here hydrogen ion concentration is given as 10 to the power minus 5, and at equilibrium hydrogen ion and A minus is equal. What can be concluded here is the dissociation constant of this acid would now be written as minus 5 divided by 0.0015. Cancel this. Minus 10, 15 by 10, 2. So it will be 10 to the 10 power minus 8. Now, by using the Oswald's dilution law, degree of dissociation is Ka by C. Sometimes I used to make jokes that alpha is root over equals to Kendra Vidyala in the class. So some of you might be knowing this. Anyway, Ka by C. Root over 4 into 10 to the power minus 6. So after taking the root, minus 3. So the percentage, in terms of percentage dissociation, it would be 0.2 because you simply divide by 100. Multiply with 100, you will be getting this percentage dissociation, that is 0.2. Clear? I hope this is understood. Let us read the next question, number 36. The correct order of increasing basic strength of the base cyanide, fluoride, and nitrite for the following dissociation constant of Ka is given as 6.2 deci and HF minus 4. Nitrous is given as quadri 7.2. So higher the value of Ka, lower will be the value of pKa, and that is higher will be the acidic nature. So since cyanide, fluoride, and nitrite are conjugate base of the acids hydrogen cyanide, hydrogen fluoride, and nitrous acid, respectively, the correct order of the base strength. I have referred to you before earlier. Remember the thumb, the rule of thumb. A strong acid has a weak conjugate base, and a weak acid will have a strong conjugate base, and vice versa for base and acids. So the sequence would now be fluoride, nitrite, cyanide. The stronger the acid will be, its conjugate base. So C, fluoride, nitrite, and cyanide would be the answer for this question number 36. Clear? Okay. Let's read question number 37. How many liters of water must be added to 1 liter of an aqueous solution of hydrogen chloride with a pH of 1 to create an aqueous solution of pH 2? So use the molarity equation M1V1 equals to M2 V2. What is the relation between normality and molarity? You have to multiply with the n factor. That relation can also be introduced sometimes if it is given in terms of normality. Never forget that equation. Okay. For this, you are given molarity 0.1 into 1, 0.01 into, you're required to find this V2. How am I getting this molarity? You might have this question. Because since the pH is 1, hydrogen ion concentration would be 0.1 molar. Because by definition, the negative logarithm of hydrogen is called pH. So hydrogen can now be written as -1. So from this, I'm getting this equation. So question is saying the pH is 1. So from this, simply get the hydrogen ion concentration. In the same way, you can also find if the pH is 2, hydrogen would be 0.0. Okay, one more decimal. This will be the second pH. So if the pH is 2, this is for pH 2, the concentration would be 0.01. This is according to the definition, that is negative logarithm of hydrogen ion concentration is called pH, right? And volume is given 1 liter each. But no, only for the first case. So you're going to find the volume of the second case. So from this again, let us look back to the molarity equation. M1V1 equals to M2V2. V2 would be 10 liters. Okay. So after 10 liters is got, you have to subtract this value again. If you fail to subtract, the answer would be wrong. So 9 liters is the answer to question number 37. I hope this is clear. Question number 38. The pH of aqueous solution of 1 molar ammonium acetate pKa of acetic acid is 3.8 and dissociation constant of base of ammonia is 4.8. Now you have to find the pKa of acid, the pH of the aqueous solution, right? So this ammonium acetate is a salt of weak acid and weak base. So if it is an acid of weak acid and weak base, what is the formula you have to use to calculate pH? Half pKw, the negative logarithm of ionic product of water, half dissociation constant of base, negative logarithm, half pKb, right? So for this, you have to multiply with the value 14 as you have from the constants, 3.8 as given in the question, minus half, this would be 4.8. Cancel 2.4, 1.9, 7. 7 plus 1.9, 8.9. Then the answer would be for 6, subtract it, 6.5. Okay, I hope this is crystal clear. Moving on to next question number 39. Solid barium nitrate is gradually dissolved in 1 quadrimolar sodium carbonate solution. At what concentration of barium ion will a precipitate begin to form? Solubility product constant for barium carbonate is 5.1, 10 to the power minus 9. So these are the given options. before we head on to the options, let us first calculate the answer. So for this question, we need to write down this dissociation of this washing soda, sodium carbonate. Sodium carbonate, if it dissociates, it generates 2 moles or particles of sodium and 1 particle of carbonate, 10 to the power minus 4 molar, 1 into 10 to the power minus 4, same, 1 into 10 to the power minus 4 molar. So the solubility KSP, let us say for barium carbonate, can be, I can write here, barium ion and carbonate ion. Fine. So the barium ion concentration would be 5.1 10 to the power minus 9 by 1 into 10 to the power minus 4. So this gets neutralized into the power minus 5, 5 into 10 to the power minus 5, approximate. So let us check for the answer. 5 into 10 to the power minus 5. 5 into 10 to the power minus 5, option A. Okay. I hope this is crystal clear and understood. Let us move on to the next question, number 40. Solubility product of silver bromide is 5 into 10 to the power minus 13. The quantity of potassium bromide molar mass taken as 120 gram per mole to be added to 1 liter of 0.05 molar solution of silver nitrate to start the precipitation of silver bromide is. So let us write the dissociation of this silver bromide. If this dissociate, we get silver ion and bromide. So what is the solubility product constant for this? Ag Br minus. So for precipitation to occur, always remember the ionic product of the solution must be greater than the solubility product. That is KSP. This is the condition for precipitation to take place. So for bromide, KSP by, we shall input the values here and check the question. 5 into 10 power minus 13, given concentration is 0.05 molar. So 5 minus 5, if this is minus 2 raised to the power minus 11. Right, so that is precipitation just starts at 10 to the power minus 11 moles of potassium bromide when it is added to this 1 liter of silver nitrate solution. So the number of moles of bromide needed from this potassium bromide would be 10 to the power minus 11. Now mass would be, mass of potassium bromide would be 10 to the power minus 11 into 120, because this is the molar mass of potassium bromide. Answer 1.2 10 to the power minus 9. B is the answer to question 40. Let us see question number 41. 3 reactions involved are given below. Phosphoric acid is diluted with water and changed to the following subsequent ions. In which of the following above does this H2PO4 minus acts as an acid? So in the first action, we have, this is considered as acid 1. Because why we are considering this? Because this water is accepting proton, so base 1. So let's say base 2. And this behaves as acid 2 conjugate base 1. And next, this is acid 1. The one which always accepts a proton is a base that you have to remember. That's the basic rule. And also remember, a weak acid has a strong conjugate base and vice versa. So this hydroxide would be acid 1 because it is losing this hydrogen. All are lost, and it is now changed to oxygen ions, base 2. So only in option 2, the reaction of this H2PO4 minus will start acting as an acid. So 41 answer would be only 2, as is evident from the reaction schemes. Question number 42, which solution has pH equals to 10? pOH is defined as the negative logarithm of hydroxide ion, that is given by Mr. Sorensen. And the sum of this pH and pOH is always 14. So for 10 to the power minus 4 potassium hydroxide, it would be hydroxide ion would be 10 to the power minus 4. Then pOH, as per the definition, it would be equals to 4. And pH, since this is given as 10, pH would be the subtraction of these two value. It will be 10. So as evident, question number 42, option A would be the answer. This is clear. Let us calculate the question 43. Calculate the pH of 0.5 molar aqueous solution of sodium cyanide. The dissociation constant of base of cyanide is 4.70. Sodium cyanide is a salt of strong base and weak acid. And the formula to find the pH is pH equals to 7 plus half dissociation constant of acid, pKa, plus half of log C. And pKa for hydrogen cyanide would be 14 minus 4.70, would be 9.30. Now let us input all these values here. 7 plus 1 by 2 into 9.3 plus half log of 0.5. Substitute the values and you would get the answer near to 11.5. This would be the answer for question 43. 44, for the following reactions, 3 reactions are given, A, B, and C. The equilibrium constants are given as K1, K2, K3. So since they are overall subsequent reaction, what you have to do is you need to multiply the intermediates. K1 and K2 is obtained from K3. So the overall equilibrium constant would be multiplication of the first and the second equilibrium constant. So K3 is equals to K1 into K2. So looking at the options, C is the appropriate answer for question number 44. I hope it is clear and understood. Now, as usual, you solve this question number 45 and try to give the answer in the comment section. Thank you for joining up to them. We shall meet for the last episode tomorrow on thermodynamics, after which there will be overall question analysis starting day after tomorrow. Thank you.